Welcome back to Real Analysis. We're going to continue our work in Chapter 5, looking at more and more results that are familiar from our calculus experience. In this section 5.8, we're going to be taking a look at the intermediate value theorem. Maybe you want to stop the video right now, grab your calculus book, flip to the intermediate value theorem in the index, find what page it's on, and check out how it was presented to you there in your calculus book. We're eventually going to state and prove the same theorem here in this video. Okay, so we're going to start by talking about what we mean for a function to have the so-called intermediate value property. Okay, so this paragraph that we're looking at here is saying under what conditions a function defined on some interval has the so-called intermediate value property, or IVP, on that interval. All right, so let's just kind of check it out, and there's a picture that we can look at as we're narrating it. So it has the intermediate value property on the interval if whenever you pick two inputs in the interval. In the picture down here, it looks like A is less than B. So one of those two inputs has to be less than the other. So why not draw it like that? But then we're going to insist that the outputs are not equal. Okay, so f of A and f of B are two different numbers. F of A doesn't have to be bigger than f of B, but it can't equal f of B. Only got one picture, so it was drawn like f of A is bigger. Okay, and then the universal quantifier is when you pick any element D, any number D that's between f of A and f of B. F of A and f of B aren't the same, so it's possible to pick numbers between them. And this is saying that no matter how you pick it, so no matter where in this interval on the y-axis between f of A and f of B you choose this value D, if it's the case that there's always some input value C, so there always exists a number C between A and B whose output is D. Okay, so if I kind of complete the picture here, you can see the dot there, but I'll just sort of draw a dotted line. So no matter where I choose that D, I can always find an input C between A and B that maps to D, then I'm going to say that it has the intermediate value property. Okay, so why is that a reasonable name? It's because we're saying that F takes on all values in between any two of its values. F of A and f of B are any two distinct values, and D is any number in between them. So if it takes on that value somewhere. So it takes on all values between any two of its values. If it does that for all A and B on I, then we say it has the intermediate value property on I. Okay, so it can't skip any values in between any two of its values. So the main theorem that I want to prove, the theorem that you saw in calculus, the intermediate value theorem, which will give kind of a similar acronym, except it's going to be the IVT. The intermediate value theorem says that if you take a function on that interval and it's continuous, then it'll have that intermediate value property. All right, so sort of kind of in chalkboard notation down here, I've stated, what does the intermediate value theorem say? Continuous functions have the IVP. If you're continuous on an interval, then you have the intermediate value property on that interval. Okay, and you use this theorem quite a bit in calculus. We're going to get a kind of an investigation of one way you might have used it here when we prove kind of a key lemma to prove it. I'm going to kind of, before we get down to the proof, before we look at this lemma, I want to point out that the converse is false. If you tried to say like, oh, some function that has the intermediate value property on an interval is necessarily continuous, that's not true. That's not true. You can't see it super well here on the screen because I graphed this in such a thin way, but this, we've looked at this function before, this function g of x. It's this oscillating function sine of 1 over x if you're not at the origin, and it's 0 if you're at the origin. We proved in previous lectures that that function is not continuous at 0, so it's not continuous on an interval containing 0. All right, I didn't specify what interval this is here, but there's some positive and negative values, a symmetric interval around 0 that I've plotted this thing. And I claim that that function has the intermediate value property on that interval. Yeah, so the maximum value of this function is 1. Okay, takes on the value 1 actually infinitely often in that interval. The minimum value is -1. And although I'm not going to go into the details here in this video, you might want to do some of the calculations. If you pick some number between -1 and 1, that is, if you choose some value on the y-axis, the picture is very convincing. That function actually takes on the value d infinitely often in this red interval, right? There's actually infinitely many values of c for which that function is going to equal d in its output, where c is some number in the interval that I'm coloring red down there. So this function has the IVP, but it's not continuous. So our theorem, our intermediate value theorem, it's not an if and only if theorem, but rather just one implication. Continuity is good enough to imply the IVP, but sometimes functions can have the IVP without being continuous, like this function sine of 1 over x. Okay. So the proof of the intermediate value theorem will be quite short after we prove this lemma, which I'm going to give a name because it's an important enough idea on its own. I'm going to call it the location of roots theorem. Okay, so let's take a look at what it says. If you give me two real numbers, a and b, let's say that a is smaller than b, and then you give me a continuous function on the interval from a to b, who the outputs at the endpoints a and b have different signs. All right, I'm writing that just kind of compactly, that f of a times f of b is less than 0. And I say this in the proof below, but that means in particular that neither f of a nor f of b is 0. And if one of these numbers is positive, the other one is negative, all right, because their product is a negative number. So that's my hypothesis. I've got a continuous function on this closed interval. The outputs at the endpoints are not 0 and have opposite signs. So what does the theorem say? There has to be some element c in the open interval, excuse me, that f of c is equal to 0. All right. So kind of graphically, if the function's output value is, say, below the x-axis at a and above the x-axis at b, it has to cross the x-axis somewhere between a and b, right? It has to have a quote-unquote root in the interval, root being a kind of an old term for x-intercept. Okay, so I won't recapitulate the entire notation of the theorem inside my proof here, but the first remark I want to make is what I said above, that using the notation of the statement of the theorem, that it is not possible that f of a nor f of b is 0, because their product is not 0, and they have to have opposite sign. Okay, they can't both be positive and they can't both be negative, because otherwise their product would be positive. So without loss of generality, let's say that f of a is negative and f of b is positive. Okay, that f of a is less than 0 and f of b is greater than 0. If that's not the case, then replace f with its opposite, which is also a continuous function, and then proceed with the proof that I have below. Okay, so I lose no generality in assuming that f of a is negative and f of b is positive. Otherwise, I would just work with negative f. If I find a 0 for negative f, I found a 0 for f. Nice. Okay, so I've drawn a little picture here to help you follow along with the kind of main construction. So I'm going to call A equal to A1 and B equal to, or B1 equal to B, because I'm going to generate a sequence of intervals here. So that's why I'm subscripting things. And I'm just going to rename my interval I1. It's the first interval in my sequence. And then I'm going to call M1 the midpoint of it, like I've drawn in the picture down here. Okay, so A1 is A, B1 is B, and then M1 is the midpoint. My little notation up here is I'm just reminding you that f of A is less than 0, f of B is greater than 0. We're assuming it. Okay, I want to try to find a 0 in between A and B. Well, maybe it's M1. If I luck out and f of M1 happens to be 0, then take C equal to M1, celebrate, we're done. The proof is over. Okay, otherwise, we're going to do a couple of things depending on what we see here. So let me kind of use a highlight scheme. Maybe f of m1 is a positive number. Okay, so I'm just going to kind of write that above here. Maybe f of m1 is a positive number. So if that's the case, then I'm going to define a new endpoint a2. It's just going to be a1. I'm writing it down here. But I'm going to define b2 to be m1, right? So I'm going to write that right here. And then I2 is that new interval, A2 to B2. So that's what I'm going to do if f of m1 is a positive number. Okay, I've kind of tried to highlight in the picture the way I'm thinking about this. But f of m1 might not be a positive number. It might be a negative number. Okay, so if it's a negative number, then I'm going to kind of do the same thing. I'm going to set A2 equal to m1. right? So I'm going to rename M1 A2. I'm going to rename B1 B2, and I'm going to take I2 to be the interval between A2 and B2. All right, and so stop the video and make sure you kind of understand what was dictating those choices. If I have a negative number at this midpoint, then I kind of rename things so that the negative value is on the left endpoint and the positive value is on the right endpoint, and proceed with that new interval. If I had a positive value at the midpoint, then I'm always keeping the negative value at the left, the positive value at the right. Okay, and then I would proceed the same exact way, but working on the interval I2. Depending on which case I have an interval I2, and then I would do the same thing to make an I3, an I4, and so on. So I would proceed similarly to construct a sequence of intervals, I1, I2, I3, I4, and so on. And the process, if it ever stopped, it would stop if some midpoint of one of the intervals that I'm constructing is a 0. Well, then I just stop and I win, because those midpoints are going to be in my original interval from AB. Okay, if it doesn't stop, if this process doesn't stop, then I will have constructed an infinite sequence of intervals. Each one is contained in the previous one. And in fact, I can write down what their width is because I'm picking the midpoint. The width of that nth interval is half the width of the nth minus first interval. So the nth interval, bn minus an's width, would be the original width, well, divided by 2 to the n minus 1. Right? Look back up here at my picture if you can still see it. Let's just take the blue case. This interval is half as wide as the original one. So then I would do the same thing, picking the midpoint, this depending on the signs. Maybe it's going to be this side. Well, that's half as wide of half as wide, so that's a quarter of wide, and so on. All right. So I've got these intervals that are shrinking in length, and in fact, the nth one is 1 over 2 to the n minus 1 times the original of the first one. Okay, so if you got that far, I think you're going to hang with me through this proof. Just going to look at the sequence of left endpoints of all of those intervals. Each one of those left endpoints belongs to the original interval, which is a compact set, right? So the Bolzano-Weierstrass property of that compact set says that that sequence of left endpoints has a convergent subsequence. There's some subsequence ANK, and it converges to some point that's in my set, some C in my set. I'm suggestively naming its limit equal to C, because that C is going to be our winner. Okay, so I've got a convergent subsequence of these left endpoints of these intervals I've constructed, and it converges to some element C, and I know that that element is some number between A and B. Okay, in fact, I can even say that that C isn't equal to A and it isn't equal to B, because if f of A were f of A, well, I'll wait for that. I'll wait for that. So converges to some element in the closed interval. Okay. So now, by construction, remember the way we constructed these intervals, I'll use the same highlighting scheme. I always chose the A's so that the function value was negative at them. So in particular on this subsequence, A and K, f of any one of those A's is less than 0. Okay? F of any one of those A's is less than 0 for every single K. F is a continuous function. F is a continuous function and on the interval. So in particular, it's continuous at C. So if I take the limit of those f of a n k's, the a n k's converge to C. So f of a n k's converge to f of C, right? But since f of a n k is strictly less than 0 for every k, that limit is less than or equal to 0. So that's using an order property of limits. So I know that this number f of C, it's not positive. It has to be less than or equal to 0. Cool. Okay. Let's look at the corresponding sequence of B's, right? I've got this subsequence of A's, the left endpoints. Well, every one of those intervals has a right endpoint. So if I look at the corresponding right endpoint, I wrote above that for every one of those things, bn minus an is equal to b minus a over 2 to the n minus 1. So if I just add an to both sides of that and focus only on the subsequence terms, I get that bnk is ank plus the width of that interval. That would be b minus a over 2 raised to the n sub k minus 1. My handwriting's not that great there, but that's 2 raised to the n sub k minus 1. So if I take limits, take the limit using limit properties, the limit of b and k, well, it's the limit of a and k plus factor out the b minus a times that limit of the 1 over 2 to the n sub k minus 1, but that limit is 0. The limit of the a and k's is c, so the b and k's approach the same number. The right endpoints of our subsequence of intervals approach the same number as the left endpoints. I mean, that's a rigorous proof of it I just wrote down. Intuitively, it's because the width of those intervals is going to 0. So the left endpoints and the right endpoints have to approach the same number. But remember that the b's were chosen so that the function value is always positive there. Okay, so applying the limit, again, f is a continuous function. So the limit of f of b and k is f of the limit of b and k's, it's f of c. But because all those f of b and k's are greater than 0, that limit has to be greater than or equal to 0. Okay, so it has to follow that f of c is equal to 0. Okay, so now going back, I didn't write it here, but there's one little wrinkle in the proof, or one little detail rather, that I have to come up with, is that why is c, because in the statement of the theorem, why would I know that c is in fact not just in the closed interval, but in the open one? Well, it's because we said that f of a and f of b are not 0. So we proved that the c value, f of it, is 0. So c can't be a and it can't be b. So it's actually in the open interval. Nice. All right, so I hope you stopped that, and I hope you kind of appreciate how much of the machinery we're using, the Bolzano-Weierstrass property, order properties of limits, so on and so on and so on. So we've built a large amount of machinery, and now we're starting to be able to enjoy it. Okay, so stop the video and enjoy that and soak it in. I'm just going to continue along to try to keep this short. Now we can prove the intermediate value theorem. So I've just stated it again here. If you take an interval I and you take a continuous function on it, that function has the IVP on I. So continuity implies the IVP. So how's the proof going to work? Okay, well, call your interval I, take your function on it, suppose it's continuous. Let's pick a couple of points in I. I'm trying to show the IVP, so I have to pick a couple of points. Without loss of generality, I'll say A is less than B, and suppose they have different outputs, and then pick a number D that's somewhere between those two things. Okay, my goal is to try to show that D is f of something. All right, so I'm going to do this in cases. I'm actually going to leave the second case to you, but let's suppose that unlike in the picture above, that f of A is less than f of B. Okay, in the picture above, f of A was bigger than f of B. They're not equal. So as a first case, let's suppose that f of A is less than f of B, and D. So D would satisfy those inequalities. It's between them. It's bigger than f of A, but less than f of B. And then I'm going to define a new function on the interval from A to B. Okay, not on all of I. I don't need it on all of I, but just between these two numbers, A and B. And that new function is just, its value at x is f of x take away D. Okay, so that's a continuous function. Why? Because constant functions are continuous. The difference of continuous functions is continuous. So I put a little breadcrumb trail to the results that prove that. One of these theorems, I don't remember which one. I think this one says polynomials are continuous, constants are polynomials, and 540 says that the difference of continuous functions is continuous. So G is a continuous function on this interval from A to B. And then let's just check out its values at the endpoints. If we look at G of A, by definition, it's f of A minus D. That's less than 0. Why? Because we said f of A was less than D. So f of A take away D is going to be a negative number. Likewise, at B, G of B is f of B minus D. That's a positive number because we said f of B was bigger than D. So f of B minus D is greater than 0. Okay, so G satisfies the hypotheses of the location of root theorems. I've got a continuous function on a closed interval. Its values at the endpoints are not 0 and have opposite sign. So that location of roots theorem up there says that there's some number between a and b. It's actually in the open interval between a and b, if you want to be more precise, where that function g is equal to 0. But if g is 0, well, that just means f of c minus d is 0. That's another way of saying that f of c is equal to d. All right, so I'm going to leave it to you to kind of modify this proof in the case that f of b was the smaller number than d, I mean. It's a good challenge for you. You can stop the video and kind of write out that second case. So there's our intermediate value theorem. It's really the kind of location of roots theorem. The location of roots theorem is just sort of a special case where d is equal to 0. And then if you want to get any other d, if I were kind of just sort of explain the crux of the proof here, I prove it for d equals 0, and then I just shift my continuous function by d for an arbitrary continuous function. Cool. All right. So we'll just kind of enjoy a couple of quick corollaries here and then call this video a day here. So as a first corollary to this, same kind of preamble. It's kind of technical, I know. Stop the video and sort of soak it in slower, but I got a couple of real numbers. One's less than the other, function on the closed interval between them that's continuous. Okay, and this time I'm picking a d, satisfies kind of a special criteria. It's greater than or equal to the infimum of the range of this function and less than or equal to the supremum of it. Okay, continuous functions on closed intervals we've proven are bounded, right? So this infimum and supremum are real numbers. So this number that I'm writing down over here is not negative infinity, and the supremum is not positive infinity, because a continuous function on a closed interval is bounded. All right. And then so if we just apply the intermediate value theorem to this particular situation, it's saying that we can find a C in the interval from A to B that maps to D. All right, so you pick any number in between the inf and the sup, and that number is the image of something. And well, the proof of it is actually just the intermediate value theorem coupled by the fact that that inf and sup actually get assumed. Yeah, so that's from our previous work. The extreme value theorem, its number in our book is 550, says that there are numbers, x lower star and x upper star, that actually hit that. The f lower star, f of it is that infimum. F upper star is that supremum, right? We called those the extreme values of the theorem. F lower star is a global minimum. F upper star is a global maximum. And the extreme value theorem says that they exist in the interval. Okay. So if I'm going to pick something in between those things, well, the intermediate value theorem that we just proved says that if you choose D in between those two output values, F of up lower star and F of upper star, X upper star, then there's some input that hits D. So I was kind of babbling there. My tongue is dripping on me, but the first corollary is just apply the intermediate value theorem to the case where the inputs are the global minimum and global maximum of your function, respectively. That's sort of a shorter way to say it. Okay, in fact, I'm just going to kind of rephrase that. I'm calling it a second corollary, but really just sort of a rephrasing of it. Same hypotheses, same preamble, couple of numbers, one's less than the other, function that's continuous on the closed interval. Then the image of that closed interval, which I was writing above, by the way, in the previous proof, it's the same set. It just means the set of f of x's where x becomes or is an element of the closed interval. That's how I was writing it above. That image actually has to be a closed bounded interval. Okay, so just to kind of quickly walk you through the proof, and you can slow this down and kind of absorb it at your own pace. If I just name that infimum from above, little m, and I name the supremum, capital M, same numbers that we just used, then what we were just saying is the extreme value theorem means there's some inputs, x lower star and upper star, that hit those things. Okay, so there the minimum and maximum values of the function are obtained. That's what the extreme value theorem says, right? And so by the definition of inf and sup, f of anything is going to be between little m and capital M, right? So this set, the set of all possible outputs, is going to live in the interval from little m to big M. But conversely, what we just proved, if you take something in that interval, there's some element of A to B that hits it. That's from corollary 1. So that means that interval is a subset of the image. Well, two sets that are subsets of each other are equal. So there you go. The image of this closed bounded interval is a closed bounded interval. Okay, so that's where we'll stop it. Thanks for listening.